We will now check if the line L and the plane P are parallel, perpendicular, or neither. So for this, we are going to utilize the fact that is to check if the line L and plane P are parallel. We have to basically check if the normal vector of the plane is parallel to the direction vector of the line. We then say that the line L and the plane P are parallel. And correspondingly, if normal vector of plane is perpendicular to the direction vector of line, then we say that the line L and plane P are perpendicular. So let's see how to determine this. So first, for this given plane, I'm going to determine the normal vector. So I can write down this normal vector in component form as we just have to pick this coefficients, that is coefficient of x, coefficient of y, as well as the coefficient of z, and put them as a component of the normal vector. So the normal vector is 2 comma 3 comma negative 1. We put this in component form, and I also write down this direction vector. So direction vector, I can write down this in component form as 2 comma 3 comma negative 1. And to determine that if these two are parallel, basically we have to check if either of the vectors can be written as a scalar multiple of another vector. So clearly we can see that d vector is basically the scalar is 1 here. So 1 times of normal vector. So we can say that these two vectors are parallel. And this means the line L and the plane P are parallel. Let's do part B. So here we have the plane 4x minus y plus 5z equals 0. So first I'm going to write down the normal vector of this plane. And this equals, we have to write down this in component form by taking the coefficients of x, y, and z. The coefficient of x is 4. The coefficient of y is negative 1. And the coefficient of z is 5. So this is the normal vector, and let me write this direction vector of the line, that is 2 comma 3 comma negative 1. And we will see if these two are parallel first. So if suppose they have to be parallel, then we have to write either one of the vectors as the scalar multiple of another vector. Let's see if we multiply this direction vector by 2, and if we do that, we get 4 comma 3 times of 2 is 6, and negative 1 times of 2 is negative 2. So if we multiply by 2, we get the first component as same as that of the normal vector, but the other components are not the same as we have obtained over here. That is, the other component has to be 6. However, we have negative 1, and the other component has to be 5. uh, I'm sorry, this has to be negative 2, but we have 5 here. So n vector cannot be written as a scalar multiple of d vector. So we write down this n vector is not a scalar multiple of d vector, or vice versa. Otherwise, we can also see that d vector is not a scalar multiple of normal vector. And this means these two vectors are not parallel. So therefore, we say that the lines L and P are not parallel. And this means we can check if these two are perpendicular. So to check if these two are perpendicular, we have to utilize the dot product. So I do the dot product of n vector with direction vector d vector. So let me substitute this normal vector, that is 4 comma negative 1 comma 5, and this has to be dot with the d vector is 2 comma 3 comma negative 1. So we just have to multiply the corresponding components, that is 4 times of 2, and this equals 6, plus negative 1 times of 3, that is negative 3, plus 5 times of negative 1 is negative 5. I'm sorry, 4 times of 2 is 8. So let me correct this. This is basically 8. So we now see that this we have 8, and negative 3, negative 5 is negative 8. So we get 8 minus 8 equals 0. and this means the dot product is 0. So that implies the vectors normal vector and d vector are perpendicular. So according to this fact, since the normal vector and the direction vector are perpendicular, the planes, the lines L and plane P are perpendicular to each other. Let's do part C. So here we have the plane x minus y minus z equals 4. So first let me write the normal vector, and this equals, we take the coefficients of x, y and z, that is 1 comma negative 1 comma negative 1, and I also write down the direction vector. So we have d vector equals 2 comma 3 comma negative 1. Let's see if these two are parallel to each other. So for that, we'll see if one of them can be written as a scalar multiple of another vector. So when we compare the first two components, that is, we have one here and we have two here. So clearly, this t vector, suppose if this has to be parallel, the scalar multiple has to be 2. So only if we multiply this 1 with 2, we get 2. And this means every other component should also be multiplied with 2. So if we have to multiply this by 2 as well as this by 2. So when you do that, that is this normal vector, if you multiply that by 2, that is 1 minus 1 and minus 1. So 2 times of this will be 2, and then 2 times of negative 1 is negative 2, and 2 times of negative 1 is once again negative 2. So basically we should get the d vector as this, that is the 2, negative 2, negative 2. Only then we see that these two vectors are parallel. However, our direction vector is 2 comma 3 comma minus 1. So these two are not equal. So therefore we see that n vector cannot be written as a scalar multiple of the direction vector or vice versa. So we can also see that the direction vector cannot be written as a scalar multiple of the normal vector. So clearly these two vectors are not parallel. Now let's determine if these two are perpendicular. So we will do the dot product of these two vectors, that is n vector dot with the direction vector of the line. So let me substitute this. 1 minus 1 minus 1 is the normal vector, dot with the direction vector is 2, 3 comma negative 1. So we find the product, corresponding products, that is 1 multiplied with the 2 is 2, plus negative 1 times of 3 is negative 3, and then negative 1 times of negative 1 is positive 1. So this becomes positive 1. We see that this is 2 plus 1 is 3, and then we have this negative 3. So this gives us 0. And this means the dot product is 0. So therefore these two vectors are perpendicular to each other. Since the normal vector is perpendicular to the direction vector, and according to this fact, we see that the line L and the plane P are perpendicular to each other. We now do part D, that is, we have the plane 4x plus 6y minus 2z equals 0. So first let me write this normal vector. So this equals the components of x, y, z, that is 4 comma 6 comma negative 2. And let me write the direction vector of the line, that is d vector equals 2 comma 3 comma negative 1. Now we can see that we can write this normal vector as twice of the direction vector. So suppose we take this direction vector d and we multiply this by 2. So this equals 2 times of 2 comma 3 comma negative 1. So we have to multiply all the numbers by 2. So 2 times of 2 is 4, and 2 times of 3 is 6, and 2 times of negative 1 is negative 2. And clearly this is the normal vector. So we see that 2 times of the direction vector equals the normal vector. So this satisfies the condition, that is normal vector is written as some scalar multiple of the direction vector, and this means these two vectors are on the same direction. So therefore we see that these two vectors are parallel, which means the line L and the plane P are parallel to each other. And so we have answered all parts of this question.